1.5, continuity. In this lesson, we're going to learn what it means for a function to be continuous. Looking at a graph or a curve, continuous simply means that you can draw that curve without lifting your pencil, as I just did. If I have to lift my pencil because of an asymptote, then with that x value, at this value of a, we say the function is not continuous, or we say the function is discontinuous at x equals a. We can also have another kind of discontinuity. If we have a hole in a graph, we would still say x is discontinuous at x equals a. And the other common thing that we see is a jump. Maybe it stops there and then starts back up somewhere higher. If that value is a, we would say we have a discontinuity at x equals a. And we're going to see all this in detail. At the top of this slide, you see more of those examples of discontinuities at various points. All of those points were labeled C in this example. And then below, we're given the formal definition of continuous. To be continuous at a point, you need to meet three conditions. The function has to be defined at that point. The limit as x approaches that value has to exist. And the conditions 1 and 2 have to yield the same number. This is the only one we really care about too much, because if condition 3 is true, it already implies that condition 1 and condition 2 are true. You can't say two things are equal if they don't exist. So condition 3 is the one you're really going to have to memorize and be able to use. Find a limit value, find a function value, see if they match. This first example gives three different functions that are pretty similar. All of these you should know how to graph from pre-calculus. The trick to graphing all of them, since they're kind of similar, is to factor the top. And we notice this x minus 2 factor cancels out, so we have a hole at x equals 2. And that's what we see in this first graph, a hole at x equals 2. So no, it's not continuous at x equals 2 on this first one. Part B tries to fill in the hole by saying put a dot at y equals 3. The function value then becomes 3, but the limit becomes 4. These two numbers don't match up. In more detail for that part B there, we would say limit as x approaches 2 of the function. Y gets close to 4, but f of 2 itself is equal to 3. Since these don't match up, we say no, this is not continuous at x equals 2. Part C for the h of x fills in the dot right at 4, which makes the limit and the function value equal to each other. And that's it. If you thought you were going to get lucky and catch me in a mistake, I did catch my own. This should not have been an f of x. This was a g for the second function. Almost got me though. Next, we've got a couple of graphs of continuity in real-world applications. First one we see the x-axis, well, they call it the t-axis, would be time. Y-axis would be voltage. And it looks like we're representing some kind of electrical piece of equipment. Current stays in there, but as soon as you cut the power, current drops down or voltage drops down to nothing. That would be a discontinuity because at one point we had voltage, then suddenly we did not. Same thing happens with store inventory. When you restock your store, you might have dwindling supplies, but then the next day restocking happened and you're back up to the top. So that would be an example of discontinuity too, like a store selling a bunch of items and then getting a new shipment in. Maybe we go down to having 5 items left, but the next morning we suddenly have 30. So far we've only talked about continuous at a point. We can also talk about continuous on an interval. a closed interval. And it means pretty much what you'd expect it to mean. If it looks like every point on that interval is continuous, then we say we're continuous on that interval. That's it. Instead of saying continuous at a specific point, we can say continuous on the interval a to b. And notice the limit doesn't even exist from the left or the right for b, or from the left on a. So you can't really say the limit exists at a or b, but we get to fudge it a little bit, and we get to say that we're continuous from the right at a, and we're continuous from the left at b. So when we're looking at the right of a, we're good. From the left of b, we're good. Then we get to say we're continuous on that interval. We don't really care about what's on the other side of the endpoints. So in other words, it really just works out the way you want it to. Next up says, what can you say about the continuity of the function f of x equals 9 minus x squared? And hopefully by this point in your math careers, you can look at that and say, oh, that's a circle. If you don't believe me, follow along on the steps I go here, and you should see that it's a circle. Once we put this in standard form, we see this is a circle with center 0, 0, radius 3, except it's only the top half of the circle. To get the bottom half of the circle, we would have had to have y equals negative 9 minus x squared. That's how we get this graph over here, top half of a circle. And just looking at that circle, we can say that it looks like it's continuous starting at negative 3 and stopping at positive 3. So we say continuous on negative 3 to 3. And those are x values. We always talk about x values when we're talking about continuous. We want to know what values of x work. This next theorem tells us some things that we also want to be true. The functions f and g are continuous at a specific point, and their sum is continuous at that point. Their difference is continuous, their product is continuous, and their quotient is continuous as long as g of c does not equal 0, because guess what? You can't divide by 0. In fact, if g of c is 0, we automatically know we have a discontinuity because you are never allowed to divide by 0. You can't plot that point. We know this. You have to kind of be able to visualize what that would mean on a graph. If a function is not defined at 0, then it can't be continuous at 0. This next theorem tells us some more things that we're going to be happy to know forever. Polynomials are continuous everywhere. Think about what a polynomial looks like. They never have a hole. Rational functions do have holes. They also have asymptotes. And part B says rational functions are continuous everywhere where the denominator is non-zero. If you remember, if the denominator was 0, that's where you get your holes and your asymptotes. So in other words, rational functions are continuous everywhere that you don't have a hole or an asymptote. And that kind of makes sense if you just sketched some random rational function with some asymptotes. You might have something like this, might have a hole somewhere, might have another hole. Those are all places that the asymptote, or where the denominator would have equaled 0. Example 3 asks, for what values is there a discontinuity in the graph? And I gave you the graph, so we're going to do this two ways. First, let's look at the graph. Pause the video for a second and try to guess where the two discontinuities are just by looking at the picture. I'm telling you right now there's 2 of them. And I'm looking for x values. How do I know I'm looking for x values? It says for what values of x. Pause now. If you said x equals 2 and x equals, I think that's a 3, then you are right. We have an asymptote at x equals 2. We have a hole at x equals 3. We're not continuous at those types of points. Let's do the same problem algebraically. If I didn't have the graph, you might have started by factoring. In fact, pause the video, try that on your own. Our theorem on the previous slide said we're not continuous anywhere where the denominator is 0. That happens at 2 and 3. We don't even have to know where the hole is and where the asymptote is to tell where the discontinuities are. Yes, we should know that there's a hole at x equals 3. Yes, we should know there's an asymptote at x equals 2. But to answer this question, we don't have to figure all that out. We don't have to draw the graph. Next up, we're given the graph of y equals the square root of x. Looking at the picture, we should totally believe that this is continuous everywhere. A couple reasons. One, the function value exists everywhere. There's no place that this is undefined. That was condition 1. We had to worry about defined. The limit exists everywhere. And the easiest way to tell something's continuous is, can you draw it without lifting your pencil? And we can. Unfortunately, I'm going to expect you to be able to do this without looking at a graph also. None of the theorems that I've given you so far talked about absolute value at all. They talked about polynomials. So what we're going to do is take this absolute value graph and rewrite it as a piecewise function with polynomials. Go ahead and try that. Make it 3 pieces. Hopefully you're okay with coming up with something like this. For x, our critical number was x equals 0. So I had to split into 2 pieces. One for x is bigger than 0, one for x is less than 0. Plus I have to take care of the case where x is exactly equal to 0. If x is bigger than 0, then we don't need the absolute value sign, so I just wrote x. If x is smaller than 0, we need to put a negative sign in front of our number. For instance, if x was -5, we want +5 to come back. So we'd want something like this. Negative of -5 makes +5. And then we could have put something like this to take care of the x equals 0. You don't have to. Here's our piecewise function. Now let's examine the condition for continuous. We need the limit as x approaches 0 to equal f of 0. F of 0 is the easy part. We get it from line 3. It's equal to 0. Limit as x approaches 0, a little harder. We have to look at the left and the right. When I'm looking at the right, that's this top one, plug in 0, I get 0. When I look at the left, look at the second one down, plug in 0, still get 0. So my limit is 0. You can verify that also by looking at the graph itself. From both sides, our graph gets close, our y value gets close to 0 when x gets close to 0. So here's our condition for continuous. These two have to be equal. It happened. We also know that y equals x is continuous everywhere, y equals -x is continuous everywhere. 0 is the only place that we had an issue. Had to be careful there. We're now continuous everywhere, so we're done. Continuity of compositions is another thing that just works out nice. As long as we're trying to find this limit as x approaches c of f of g of x, first we need to make sure that the limit as x approaches c of g of x exists. It's going to equal some number. And then we can plug that number into L, or we can plug that number L into the f function, just like we want to. So we can kind of distribute. Distribute is a bad word. It's not really distributing, but it's putting it on the inside. And that works. Also, one of the nice things, if two functions are continuous everywhere, then their composition is also continuous everywhere. Another thing worth pointing out, if you have an absolute value of a continuous function, the original function in this case would be y equals 4 minus x squared. absolute value of that is just going to reflect across the x-axis. And that'll always be continuous also, because all you're doing is bouncing instead of going through. You don't have to lift your pencil. You have to be careful around these points, but it's always going to work out. Alert, alert, alert. This is probably the second most important thing from this lesson. Knowing what continuous means being the first most important, this is a close second on things you have to know, things that often show up on an AP test, things that will probably show up on my test. It's called the intermediate value theorem. It says if a function is continuous on a closed interval, in this picture's case, the interval is a to b, and then k is any number between f of a and f of b. Notice f of a and f of b are y values. So k has to be a number between those y values. And what this says is that the function has, if we draw a little dotted line right here, and we have a dot here and a dot here, there's no way to get from one red dot to the other without going through that red dashed line right there. It says that number always exists. So what I want you to do to kind of verify this for yourself, choose your own A, your own B, your own f of A, your own f of B. You can put a k wherever in between them. Try to put a dot, try to connect those dots, keeping it a function without going through that dotted line. If you can connect those dots and stay continuous without crossing that dashed line, I will give you an A in the class. Pro tip, it's not possible. That's what the intermediate value theorem says. Next slide, we're going to see the most useful case of the intermediate value theorem. And that useful case is where k equals 0. What this theorem says is you've got f of a is above 0 and f of b is below 0, or vice versa. Could have looked something like this, where one's below, one's above, just has to have on opposite sides of 0, those dots. If that happens, somewhere between A and B, you'll have to have a 0. Somewhere in there. It doesn't tell us where it's at, unfortunately. Sometimes that's really hard, maybe impossible to find, but it tells us that that point has to exist. And that's only true if the function is continuous on the interval. Let's look how easy it would be to draw a picture where it's not continuous on the interval and it not be true. So here's our k equals 0. Put one dot above, one dot below. If I don't have that rule that says I have to be continuous, I could just do something like this. And I never cross k equals 0. So we have to pay attention to that condition. It says k equals 0. Or no, we have to pay attention to the condition where it says we're continuous. Let me rewind a little bit. Notice that it says that. It says if f is continuous. That's how it starts. If you don't verify that continuous piece, none of this theorem is true. That is a big red flag. Pay attention to whether or not your function is continuous before using the intermediate value theorem. And we'll practice this a lot in this class. So last example. We have never learned how to solve this equation by hand. Factoring is not going to work. Rational zero theorem is not going to work. You can try it, but it's not going to work. And the only way we can maybe figure it out is by graphing this on a graphing calculator and noticing that it looks like there's a 0 between 1 and 2. And we can verify that by just looking at it. The way we can verify this using the intermediate value theorem, first off, we know this is continuous. Try to think of why. One of the theorems from this lesson. If you said because it's a polynomial, you're right. This is continuous because it's a polynomial. And we could say it's continuous on the interval 1 to 2. It's really continuous on any interval, so I can choose whatever interval I want. The only reason I chose 1 to 2 is because now I can say f of 1 equals something, and f of 2 equals something. And looking at my picture, I can tell f of 1 is going to be some negative number, and f of 2 is going to be some positive number. So we'll figure what the intermediate value theorem says is, because we're continuous on our interval, and because one number was negative and one number was positive, at the endpoints of those intervals, then somewhere, I don't know where, for some value of x, between 1 and 2, f of x must equal 0. And that conclusion comes straight from the intermediate value theorem. Let's go back to the wording of the intermediate value theorem and verify that completely. The exact wording says, if f of x is if f is continuous on a closed interval a to b, here's our f of x. We saw that it was continuous on a closed interval a to b. In this particular problem, a equals 1, b equals 2. If f is continuous on a closed interval a to b and k is any number between f of a and f of b, here's our f of a and our f of b. K has to be a number in between there. Let me say 0 because we're looking for a 0. Then there is at least one number x on the interval a to b such that f of x equals k. This is the intermediate value theorem. I'm looking for all sorts of things when you're using the intermediate value theorem. You've got to tell me what the function is. You've got to tell me what a and b are. You've got to verify that the function is continuous on the closed interval a to b. You've then got to tell me what f of a and f of b are. Ideally, one will be negative, one will be positive. That way, k equals 0 will be right in the middle. Not in the middle, but in between. Then you can make your conclusion. For some x, we don't know what it is, but we know it's between 1 and 2, f of x equals 0. It doesn't tell us how to find that x value. In fact, the only way I know how to find that x value is using a graphing calculator. This is the hardest problem in this section. It's probably one of the most important problems in this section. It's not going away. Go ahead and do your guided practice. It's super fun. Page 117. Have a nice day.